Hi there, I'm Chris again, and in this session I am showing you how to prepare your project for a time domain simulation and how to run an RMS study. In the last lesson we already built up a network and we performed a load flow calculation with that. If you haven't seen the last session, here's the network structure. We have a slack on the one side connected via a transmission line with a load bus and a generator bus. With this network, we can already run a time domain simulation. But before we do the simulation, we should do two things. First, define plotter channels so we can actually see what we are interested in. And second, define a disturbance or a network change, because without a disturbance the simulation would be quite boring. To define the channels, we can use the plot definition window, which gives us the possibility to enter channels one by one. So let's first look at all the voltages in the system. Therefore, we have to select voltage under function, instantaneous value under type, and then we have to select the node name. You can either type in the node or you use the three dots to open a list of all nodes in the project. You can choose the phase, but since we are doing a symmetrical RMS simulation, in this lesson we just keep phase R. Then you can type in a description or just push the little pen button on the right. The description should always be entered because this is the only way to differentiate the channels later. If you use this plot definition window, you do not have to touch the signal index field because it's entered automatically. So let's repeat this for the other two buses in our project. In the second step, we are defining the disturbance. The philosophy in NETOMAC is a little different than in some other programs like PSS, for example. In NETOMAC, you have to define all the forced disturbances like faults and outages before you start the simulation. Once the simulation is started, it will run all the way to the end of the simulation. So let's define the disturbance by opening the event definition window. A new event can be defined by clicking on New. The following list shows you all the available predefined event types. These events are sorted by events for stability mode, this is the RMS time domain simulation, by unbalanced stability mode, and by transient mode, which is the EMT mode. I will choose the three-phase short circuit for now. To fully define this event, double-click on it or press the Edit button. Then we need to enter the place where the fault should be applied. Let's use the bus N3, which is the generator bus. Then we need a fault duration. This is basically the clearing time. Here you see that we are actually defining two events at once. First the fault and second the clearing of that fault. So here we enter 0.1 seconds, which is 100 milliseconds. At the end, we have to enter the time until the next event. This tells NETOMAC when the next event will be initiated. Entering a very large value, such as 10,000 seconds, means that this will be the only event because the simulation will be much shorter. After clicking on OK, you see the event in the event definition window. After clicking on OK again, we are done with the two steps, the definition of the plot channels and the disturbances. Now we have to do one more check, and then we can finally start the simulation. Therefore we look at the calculation settings. Here choose the dynamic settings and go to time. In the upper part, we set the simulation time step and the time step the plot file will store the results. You can first choose the unit and then enter the time steps in the chosen unit. I like to enter the time steps in milliseconds. And as long as the simulation is not producing too much data, I always choose the same plotter time step and simulation time step. So let's set the time step to 10 milliseconds. In the lower part, we can set the simulation duration. Also here we can choose the time unit. I prefer to define this in seconds. So let's set this to 1.5 seconds. The next input is the time until the results should be stored. I would always set this to the same value as the simulation time. The third entry is important again. You might have asked yourself when the fault that we have defined earlier will be initiated. Here's the answer. In this field, we have to enter the time until the first event will be processed by the program. Let's set this to 0.1 seconds. This means that the simulation will run 100 milliseconds in steady state before the fault will be applied. When switching to the Control tab on the top, we get a bunch of other settings we can choose from. The first is the choice of which kind of simulation should be done. Here principally two main choices can be made. Stability, which is the RMS mode, and transient, which is the EMT mode. All the others allow for some special actions like switching over from EMT to RMS and the other way around. Let's for the beginning choose stability. The other drop-down fields in this tab allow for certain changes that are normally used for debugging. I recommend to use the standard settings for now. Now we have all the settings we need to perform a dynamic simulation. In order to run the simulation, we just have to select the option Dynamics from the Calculate menu. The simulation is performed fully automatically. NETOMAC always performs a load flow calculation at the beginning. Afterwards, the initial conditions are calculated, and then the time simulation runs from t equals 0 until the predefined end of the simulation. As soon as the simulation is ready, the results appear in the Signal Explorer. To draw the time curves in diagrams, we need to open the diagram window by pressing the diagram button. NETOMAC opens the diagram tab, and if not yet done, we have to create a new diagram page. This is done by pressing this button, typing a name, and selecting the page layout. There are a bunch of page layouts you can choose from. I will select now the first one that creates one diagram per page. You can add more diagram pages if you want. If not already visible, you can open the Signal Explorer with this button. It offers you all the signals we have defined prior to the simulation. Just drag and drop the signals you want to see to the diagram. The dialog allows for special settings. We can use the default ones for now. Now we see all the voltages of the three buses. We also see that the program did exactly what we wanted. Simulate 100 milliseconds, then initiate a fault, clear the fault after 100 milliseconds, and run until 1.5 seconds. Since we have not defined any dynamic data yet, the time curves are very static. So let's go back to the network data. Here we see that we only have a fixed frequency source, which is nothing else but a 50 Hz voltage source behind an impedance. To add dynamics, we need to add some machine data that brings inertia to the system. Machine data is added in the Machines section. Let's look into the help to see how to enter the machine data. You can find it under Functional Manual, Machine Data. Here you can find how machines are modeled in NETOMAC and where to enter all the parameters. Since this is not a machine modeling lesson, I do not want to explain every single entry, but I'm just copying the data from another project to my network. What we have to make sure is that the generator name in the Machines section is the same as the generator branch defined in the network section. Only if these names match, the branch will get the dynamic properties defined in the Machines section. So let's see how these changes affect the dynamic behavior of our system. Therefore, we just have to press the play button and the simulation from before will be repeated, and the time plots are drawn automatically. As you can see, our power system is now more dynamic after the fault clearing. One of the goals for power system engineers to perform dynamic simulations is to find out if the system remains stable at different fault clearing times. Therefore, the fault clearing time has to be adjusted. So let's increase the clearing time a little bit. You can do this by using the Event Definition dialog again. Here we can change the fault duration. When running the simulation again, we immediately see the results in the diagram. Another way to change the clearing time with less clicks is by editing the text file with the ending dis, like disturbance. If not available as tab, you can find it in the project browser. In this file, all disturbances you defined via the event definition dialog are stored. The clearing time is defined with this variable #t1. You can simply change the value from 150 milliseconds to 250 milliseconds and then run the simulation again. As a result, one can see that the clearing time is too large, so the system becomes unstable. So I hope I could give you an impression how to perform dynamic simulations with NETOMAC. Basically what you need is first, a network with dynamic data. Second, definition of plot values. Third, definition of an event. And fourth, definition of simulation parameters like the time step, the end time, and the time until the first event. By the way, you can close NETOMAC now, and when you reopen this project, all settings and parameters you made are still there. You can just press the play button again and you will get immediate results.
Siemens, ingenuity for life.